In today's technological era, mechatronic systems have become increasingly important in developing smart devices that improve human health and well being. A heart rate level indicator is a device designed to detect and display changes in a person's heart rate, providing information about their current condition. This project focuses on designing and developing the structure of a heart rate level indicator using computer aided drawing software. The design process involves creating a suitable casing and component arrangement to achieve a compact, reliable, and user friendly device. The primary objectives of this project are to design and develop a heart rate level indicator circuit using computer aided drawing software, to develop technical proficiency in using advanced computer aided drawing software, specifically Autodesk Inventor for mechanical modeling and OrCAD for electronic circuit and PCB design, to verify the functionality of the designed circuit through simulation and PCB layout, to independently explore and apply new tools, features, and techniques within the CAD software to enhance overall engineering skills and knowledge, to generate the PCB layout and Gerber files for future hardware fabrication. Here is the workflow throughout our mini project. We came out with the idea of designing a heart rate level indicator to monitor heart rate conditions. We studied about the heart rate sensors, indicator systems, and the designs. We identified the system requirements and designed the schematic using OrCAD software. After simulating the circuit, we ensured the indicator responds correctly to different heart rate levels. Then the schematic was converted into PCB layout and a design rule check was performed to identify layout errors. Since there were no errors, the Gerber files were exported and report was prepared.
In the mechanical part, for the body part are designed to have a slot for the piezoelectric sensor. The piezoelectric sensor is a versatile device that converts dynamic mechanical changes in like pressure, force, or vibration into electric signals. And the body part are designed in a rectangular shape and the edges are rounded to protect the user and easy to fit the wrist of the user and very safe to wear. And the body part also have a side mounting slot for the adjustable Velcro strap. For the cover part, it has a slot for the display screen. The screen part are designed as a transparent protective cover screen to protect the display screen from dust and external damages. And the cover part also have a seamless screw hole, and when the screw are insert to connect the body and cover part, the screw will not expose to the outside or hurt the user. The main body and cover of the devices uses is lightweight ABS plastic to provide a good balance between strength, impact resistance, and lightweight properties. So this ABS plastic material helps protect the internal components from minor impacts or accidentally drops and while maintaining a low overall device weight. For the wrist strap part, the wrist strap are designed, the edges also rounded, and it is a Velcro adjustable strap and can fit all wrist size. The wrist strap is made from spotting fabric material, which offer the flexibility, skin comfort, and quick drying. Compared to the traditional rubber or plastic straps, the spotting fabric improve air circulation around the user wrist, reducing heat buildup and perspiration. A Velcro fastening system is incorporated into the strap design to provide easy adjustment and secure attachment. The Velcro mechanism allowed user to adjust according to their wrist size without buckles or pin. After completing all individual components, the parts were combined in the inventor assembly environment to create the complete mechanical structure. Assembly constraints such as mat and flush were applied to accurately position and align each component parts, including the enclosure body, top cover, protective screen, and strap mechanism. The assembly process allowed me to evaluate the relationship between each component and verify the proper placement of electronic elements inside the enclosure. Interference checking and assembly verification were performed to identify the possible mechanical collisions, ensure sufficient internal clearance, and confirm that all components could be assembled correctly without modification. So in conclusion, from an ergonomic perspective, the lightweight housing and the flexible fabric strap distribute pressure evenly around the wrist, enhancing user comfort. The mechanical structure is simple and requiring few moving parts, which improves reliability and reduces maintenance requirements.
This is a schematic diagram of our circuit. The circuit is powered by a 9-watt battery and the LM7805 converts it into a stable 5-watt supply. The piezo sensor detects the heart pulse signal and sends it to the LM2917, which converts the pulse frequency into a voltage signal. Then the voltage is sent to the LM3914, which controls 10 LED. As the heart rate increases, more LED will light up to show the heart rate level. Next is the PCB layout. The components are arranged according to their functions, making the circuit compact, easy to assemble, and reliable. This is the bill of materials. It lists all the electronic components used in the project, such as the 2 capacitor, 3 resistor, 10 LED, 2 connector, and 3 integrated circuit, which is LM2917, LM7805, and LM3914. Next is the dir table. It shows the dir hole size used for PCB fabrication. Our PCB used 4 dir sites with a total of 69 dir holes for component installation and PCB mounting.
As the team leader, I managed the project timeline, organized the report, and coordinated the presentation. I also learned to use OrCAD Capture for schematic design and Autodesk Inventor for 3D modeling of the device. This improved my leadership, teamwork, and project management skills.
I designed the PCB circuit using OrCAD Capture and learned PCB routing and component placement. I also used Autodesk Inventor to assemble the 3D models and ensure the electronic components fit properly inside the enclosure. This helped me understand the integration of electronic and mechanical design.
For the mechanical part, I created the enclosure and handlebar bracket using Autodesk Inventor Professional 2026 and assembled all the parts into a complete model. I also learned to use OrCAD for basic schematic checking and PCB hole alignment. This experience improved my CAD skills, problem solving abilities, and confidence in using engineering software.
One of the main challenges was ensuring all electronic components were connected correctly and designing a compact PCB without routing errors. We solved this by repeatedly checking the schematic, verifying the PCB design rules, and optimizing the layout in CAD software. This resulted in a reliable and functional PCB. The small size of the device also made it difficult to fit all the internal components while maintaining a neat appearance. We carefully optimized the enclosure dimension to ensure enough space for the electronics without affecting the overall design.
Another challenge in mechanical part was designing a wearable device that was durable, lightweight, and comfortable. So we selected suitable materials and replaced the rigid rubber strap with a fabric Velcro strap to improve comfort, flexibility, and adjustability for different wrist sizes. And finally, we improved the ergonomics and durability of the device by optimizing the housing shape, strap width, and weight distribution. We also reinforce the strap attachment points to increase strength and extend the product's lifespan, making the device comfortable and suitable for everyday use.